Okay, then the aim is to find maximum likelihood estimates for the GLM based on the log likelihood function as we just described it. And actually we will go step by step. So we first consider the beta parameter estimation. Sorry. To do better parameter estimation first, so we essentially assume that the variance parameter is known, and we simplify the likelihood function a little bit in that we now consider the likelihood function only as a function of the beta parameter. So we don't use this product space, but we look at just as a function of the beta parameter and assume for the moment that the variance parameter is known. So this is more kind of a formality rather than something really too crucial in a way. So this is again our multivariate Gaussian here, and the first thing that we now do is to substitute the multivariate Gaussian into that. And you will know the multivariate Gaussian by the exam, so I'm just writing it down now. So this formula is just the multivariate Gaussian for a spherical covariance matrix. So because in the normal, of course, multivariate Gaussian, or in the general multivariate Gaussian, you have this inverse determinant in this normalizing factor, but because the determinant evaluates to n times sigma square here, you get this kind of simple normalization term, and then you have the exponential term, and also here the inverse of the covariance matrix is accounted for by this 1 over sigma square parameter, and here you have the x beta t y minus x beta. So again, this formula you get just by putting this error covariance matrix in the standard form of the multivariate Gaussian density, and then you have immediately this formula. So if you're confused about this formula, make sure that you are happy with the multivariate Gaussian. And then we can do a log transform of that immediately. So to get the log likelihood function for the beta parameter now only, so that's our Ly beta. And this should now be the, I can write it out, the log of this we just wrote down. So any suggestions for the log of this first factor here? So if we take log 2 pi sigma square to the power of minus 2, what do we get? So what does the log do to exponents?
Rejects it or cancel it out with each other?
No, don't cancel it out. It's not. So I'm not talking about the exponential right now. I think that's what you meant. So I'm talking about this. If you have log a to the power of b, what do you get?
minus b times n.
Yeah, exactly. So you get here minus n half times log 2 pi sigma square. And what can you do with logs of products? So if you have log a times b, what do you get? Plus what? Exactly. So this is then usually, because we will also be interested in this, so we take this out of this term so that we have one isolated term for this. So we can write this as log 2 pi, which is independent of beta and sigma square. So for maximization, this term can be neglected. If you compute the derivative with respect to beta or with respect to sigma square, this of course goes away. And we have minus n half ln sigma square. And then, as you already said, for the exponential, so if we take the log of this term here, so the exponential term, then they cancel out. So log x is x. Let me briefly finish this here. This is b ln a. So we get minus 2 sigma square y minus x beta t y minus x beta. So that's now our log likelihood function that we want to maximize with respect to beta in this case, and then later also with respect to sigma square. And yeah, so essentially we need to compute the derivative. And now what we do essentially next, just to make this kind of very clear conceptually, what we essentially do next is the same thing that you did in school for something like this. So if this is x square, for example, then you compute it. So your function is f x is x square. Then you computed the first derivative of this, which is obviously 2x, and then you set the first derivative to 0, and then you solved for x, so you divided by 2 and you got 0. And obviously this is in this case the minimum. Could have shown something with the maximum, but this is now what happens. It just looks a little bit different, so just keep that in mind if you feel confused. So essentially we just compute the derivative and set to 0. If we do this, we have the first thing that we notice is that actually this beta is a vector. So I think you are familiar with computing derivatives, I hope, with respect to scalars. So if you compute the derivative of this function with respect to x, then you know how to do that. With vectors, it's a little bit more involved, and actually there's a whole kind of vector calculus thing. The essential generalization that you need to make here for the beta vector is that essentially if you want something like the derivative of the log likelihood function at location beta, that is the gradient of the log likelihood function with respect to beta, and the gradient is the vector of all partial derivatives. So if you compute the derivative of this function with respect to beta 1, that's the first entry in the gradient vector, and the second entry is the partial derivative with respect to the second beta, and so on until the pth beta, because there are p parameters. And the equivalent condition to setting the derivative to be 0 is to set the gradient vector to 0. So to set this to 0p, so a p-dimensional vector. And with the partial derivatives, just remember that the partial derivatives are just the standard derivatives that you know from school. So you compute the derivative with respect to a single number or single variable, while all the other parameters are constant. And so this is now the same thing as saying that the derivative is 0. And if one computes this, actually, so if one computes the gradient of the log likelihood function, then one can show, and I will show you that in the script without writing everything down, that one gets to an equation that looks like this. Which is called also normal equation. It's a little bit of a weird name, but that's what it's called, normal equation, normal equations. So what I'm saying here is that, get rid of that, derivative of the log likelihood function so the gradient of the log likelihood function equal to the p-dimensional 0 vector is the same thing as saying that the design matrix times the design matrix times beta equals the design matrix transpose times the data. Yeah? So that these statements are equivalent, and I will show you why they are equivalent in a second. But if one has this equivalence, then of course one can immediately solve this here for beta. So you can also write this, maybe that gets a little bit clearer. Of course, we are now stating at the location of the maximum likelihood. So if at the location of the maximum likelihood, the gradient of the likelihood function with respect to beta is 0, is the 0 vector, and this is equivalent, of course, to the fact that the design matrix times the design matrix times this location is equal to the design matrix times the data. Yeah. So this equivalence here, for the moment, you have to believe me. I will show you that in a second. But besides that, is that clear? No, it's just saying this equation. So saying that the gradient at the location of the maximum likelihood estimate is 0 is the same as saying that this side here is equal to this. And then one can, just by multiplying both sides with the inverse of this, matrix, so this x times x matrix is of course a p times n times an n times p dimensional matrix, so this is a p times p dimensional matrix. And if X is a good matrix, essentially, then one can compute the inverse of this matrix, and then one gets this. And here you have the inverse of xtx times xtx. What does that yield? Yeah, or the identity matrix, so the p-dimensional identity matrix. And if it's 1, then we can of course also not write it. So our maximum likelihood estimate is then given by this formula. And this formula is actually also known as the ordinary least squares estimator. It's now not, I didn't introduce it like this, but it's also known as this. But it's so the maximum likelihood estimate for the beta parameter and the ordinary least squares estimator are the same thing, also known as Gauss-Markov estimator, although my reviewer didn't like that. And that's already our first maximum likelihood estimator. So note what we have here. So we have a formula if we have some data, y, observed data, then by multiplying it essentially with the design matrix and the inverse, so essentially by multiplying it with this here, which is also known as the pseudo-inverse of the design matrix, of x, we get the maximum likelihood estimate. Yeah? So the design matrix we of course know, and the data we know, so we can always compute this better parameter estimate. Of course, this result crucially rests on this here, so that actually these normal equations follow from setting the gradient to 0. And this I can show you in the script, where I wrote this down a little bit and already this morning found a typo. So there's this little proof here, 937. So we're starting with the idea that the gradient is 0, and we somehow want to solve for the beta. Because that's the necessary condition for an extremum, like our first derivative equals 0. And this implies that all these individual partial derivatives are 0. And there's a typo, so it should be the partial derivative of this with respect to bj equals 0. Because this is what's here, so the cp is of course just 0p is just a vector of all zeros, so all of these partial derivatives are zeros. And then one can continue with what that means. So what does it mean that this partial, or all these partial derivatives are 0, by looking at one of them, and then what is substituted here is the log likelihood, and what I also left out already is this log sigma square term, because if you compute the derivative with respect to beta j, of course this term here is going to 0 and this term is also going to 0, so I'm only looking at a term where the beta is involved, so something that is not immediately 0. And then we also, if this is 0, we already know that the second term, so this partial derivative here, or 1/2 partial derivative, is equivalent to 0 because sigma square cannot be 0, so this must be 0. And then one has this equivalence, so far so good, and then one actually has to compute a little bit. So if one now evaluates this, so what I'm doing here is first writing this vector product in terms of a sum of all the deviations of the data from the predicted data, and then actually computing the derivative using chain rule, and then this 1/2 also goes away. Then what am I doing next? X beta. Where do I get this minus sign from? I'm not quite sure. But essentially, I basically write out more and more these individual sums. And if you write them out more and more, so it's all about indexing and writing out what is actually behind this, then you end up with these expressions. So it's a little bit more fun if you go really over it step by step, but the general idea is that you write out these matrix multiplications, and then you have this one equation that looks like this, and this equation, if you look at that now for all beta parameters, then you can again look how these sum and multiples look, And it's not that fun talking about it like this, but also writing it out is not that fun. So the most fun is if you go over it step by step. Then you can turn this representation into a matrix product. So this is what I'm doing with the left-hand side here. So the left-hand side is reformulated as this xt x beta, and then I'm doing the same thing with the right-hand side. So these terms here are turned into this, and then this x times y. So it works by zooming in, essentially, so to go from the gradient to the normal equation. It works by at one point computing the partial derivatives and then zooming in, looking at all the elements, and then zooming out again by formulating this as normal equations. It's actually very similar to what you do in what everybody loves, of course. Backpropagation in neural networks also works like this, but that's something for the summertime. Yeah, so one can understand, this is what I'm trying to say, one can understand where this equivalence between this and the gradient being 0 comes from. One just needs to zoom into the matrix products. Yeah, and so if you want to really learn about this, then I would suggest going into that in some detail. I think there's a minus sign missing. I'm a little surprised by this minus. But maybe you also find a typo on that. But that's how that works. Good. But the bottom line is this equivalence holds. These are the normal equations. Solving the normal equations then give a formula for the beta parameter, and that's our beta parameter maximum likelihood estimate. Now that means we already have our beta parameter maximum estimate. If you look into the script, then I think after this section there's a discussion of why this is equivalent to ordinary least squares. So what you mentioned earlier, it's essentially because this thing here, this is of course the squared deviation between the data and the data prediction, and this is what you usually refer to squared deviation, and minimizing this is then least squares. Yeah. And this is essentially the reason why this is equivalent. So what is left to do is then to come up with a variance parameter estimate. Yep.
I mean, this looks so easy that you can just calculate the parameters now. Why people then do the numerical?
Yeah, a good question. So for this is one point here for the GLM in this setting. So when you have if you model your data really like this, then you can, and this is also what people do, you can really just use this as your formula and have your parameter estimate. The thing is if the model becomes more complex, then often there are no analytical solutions available, and we will see that definitely when we talk about covariance components, when we have, and then it's firstly mainly about the variance parameters. So if the covariance matrix here becomes a little bit more complex and you have multiple terms, then computing the derivative and this equivalence and then solving is not that easy anymore. And then you also get couplings between the beta parameter estimates and the variance parameter estimates, and then you need numerical schemes. So if you just have a GLM in this setting, then you don't need to do anything numerical.
Can you then just repeat when, I mean, is this always for our fMRI data, or is it just a special case now? Because
no, this for the fMRI. So what this is essentially what So for fMRI data, it's actually different. For fMRI data, what we will introduce are error correlations and then the variance, covariance matrix, and this is what we will do. Then next time it looks more complex, so that will look more complex. But this scenario that we have here is the case of independent and identically distributed errors, so independent data points. And this is, of course, most of classical statistics, the assumption. So if you have, for example, if you implement a t-test or linear regression or an ANOVA with independent identically distributed error terms, then you always assume this, and then you can always have analytical solutions for your beta parameters. Yeah. Any other question right now? Good. So what is left to do is actually to find the parameter estimate or maximum likelihood estimate for the variance parameter. And the way that this is typically done, which is also a bit of a problem, is that one maximizes the likelihood function with how can I say that? What we however, in whichever way one does it, the estimate for the variance parameter will depend on the beta parameter. So we can either compute the variance parameter assuming that we know beta, or we can also already plug in a beta head. Either way, we will get a formula where the variance parameter estimate depends on beta. And then, of course, in real life, we don't have beta available. So what we usually then do is use our maximum likelihood estimate for beta in the estimation of the variance parameter. And this is then the maximum likelihood estimate. But it also, of course, has a problem because we use an estimate to evaluate another estimate. So by this, we introduce some error. But let me just proceed by now looking. Maybe we do it a little bit different than in the script. We now assume that beta is known. So assume beta known. And we look at the log likelihood function with respect to the variance parameter. So we only have the log likelihood function as a function of sigma square. So sigma square gets mapped to Ly sigma square. And of course, this function is exactly the same as previously. So that's our log ny x beta sigma square in. And this is, of course, exactly the same as we evaluated earlier. And now again we need to compute the derivative. So and here there's no further tricks in terms of gradients or so on, because this is just a scalar parameter. So if we compute the derivative of the log likelihood with respect to this, then we get this term goes away, and here we get the derivative of logarithm, which is what? What's the derivative of log x? Exactly. So we get here n divided by sigma square, and here the same thing. Only that, no, sorry, not the same thing, because we have, sorry, here we have 1 over x. So what's the derivative of 1 over x?
divided by x squared.
And there's one other thing.
And half.
So we have this, and then, so you, why a half? It's not x squared. But so what you said so far is, so if you compute the derivative of this, what you said so far is this, but there's one more thing. Now if you do this, what do you get? Yeah, and what did you do? Yeah, exactly. Sorry. Yeah. Because I already put that here, so this is why we have the plus here, and then we get 1 over sigma square. So you need to understand, or sigma square here is a symbol. So with the square, you could also put, for sigma square, you could, I don't know, put a rho or something, and then you would have 1 over rho square. So yeah, that's just how it is. And then of course here you have still the y minus x beta t y minus x beta as the factor. Well, yeah, it's a little bit of a longish proof in the script for that. It's actually not that complex as I make it there. And then this needs to be set to 0. So yeah, if we see that we want to set this to 0, we then of course already see that we get an equation of the form 1/2 1 over sigma square y minus x beta t y minus x beta equal to 1/2 n over sigma square. So this was a plus here. So setting this to 0, basically if this thing here is 0, then of course we can take this minus 1/2 n sigma square to the other side, and then we get this equation, and then we just need to continue to solve this for sigma square. We might as well already put in that this holds at the location of a maximum, because it's again the necessary condition for a maximum. So this again holds for the maximum likelihood estimate, for which I can also put the ML down here. And so we need to now solve this for the sigma square maximum likelihood estimate. So we can multiply both sides by 2, then we get rid of that. And then we can multiply, oops, the 1 doesn't go away. Whatever. So now it's away. And then we can multiply the whole thing by this, for example. So then we get y minus x beta t y minus x beta being the same as sigma square NL square divided by sigma square NL and n times n. Let's put this up here, it's a bit clearer. So then 1 of the sigma square of course cancelled us out, so we get rid of that. And then we can divide the whole thing by n, and then we're already there. So we have sigma square NL equals y minus x beta t y minus x beta divided by n. Yeah, and so that's now our maximum likelihood estimate formula for the variance parameter. The problem with this formula is, yeah, as I already mentioned, that it rests on this beta, and the beta we don't know, but we have, of course, a maximum likelihood estimate for it. So in real life, of course, then we would use sigma square ml being y minus x beta hat ml t y minus x beta hat ml divided by n. And yeah, so this is then the maximum likelihood estimate for the variance parameter. And it's interesting because, first of all, it is based on the residuals. So if you have your beta parameter estimate and you multiply it by your design matrix, then of course you make your best prediction of the data. And what you evaluate here is essentially the least squares. So you or not the least squares, the squares, the remaining squares, the residual errors. So you have your data minus the prediction of the data based on your beta parameter estimates. You square these deviations and then you divide them by n. So the remaining deviations are your estimate for the variance of the errors. And the problem with that is, of course, that you have not fully you don't have full knowledge of beta, so there is some variability in your beta estimation, which actually makes this estimator biased. So this maximum likelihood estimator is not the best estimator you can get. So in real life, what is actually used is not the maximum likelihood estimator, but I think, yeah, how do I call it here? It's actually the restricted maximum likelihood estimator. So you subtract from n the number of parameters, and that's then the REML estimator. The REML estimator, so the restricted maximum likelihood estimator, with this n minus p, follows from the idea of restricted maximum likelihood, and we will also discuss that. For the moment, we might as well stay with the maximum likelihood estimator, knowing that this is not an unbiased estimator. If you want to understand the whole thing of bias and unbiasedness and estimator quality statistics for data science this week and next week, that's why we discuss this. But for what we want to do, I think I'm happy. So we now have, to summarize, we now have established that our data is distributed according to this. And we have obtained maximum likelihood estimates estimators for the parameters, namely xt, x minus 1, xt, y, and our variance maximum likelihood estimator 1 over n, y minus x beta hat ml t y minus x beta hat ml. Yeah, so we can now, whatever we have for x, we can simulate and always estimate our parameters. And that's all I wanted to do today. Questions about this? No. So the data goes in here, and then of course the data goes in here as well. You can start thinking about what this formula actually means, so how you get from the data to the beta parameter estimates. So the question is, what does it mean to multiply the data with the design matrix? And if you think about it, then you get intuitively to the point that so if you transpose the design matrix, you get of course a p-dimensional or p-row matrix times n columns, and you multiply each of these rows with the data, and if this value is large, this of course gets large if there's quite some similarity between the data and that line. So if the regressor looks a lot like the data, you get a large number for that in this thing here, and then you normalize it by essentially the not autocorrelation, but the self-correlation of these regressors. So if they if the regressors in general are very large, you account for that in this. So this is a way to understand what's going on with respect to the beta parameter estimate. And then of course the variance or the remaining error gives you your variance parameter estimate. Good, so if there are no questions, then we stop here, and then next week I think I will do generalized least squares estimation, because for the random process stuff still have to work a little bit. So I think then next week we will discuss what we can do in terms of this estimation if we go to other covariance matrices that are not of the spherical form, and why we exactly go to this we will then establish at a later time point, why these forms of the covariance matrices are a good idea for fMRI data. We will do that at a later point then. Yeah.
I have another question. We have, like when we gather some data, we always have an error, right? Like we can...
What do we have?
We have an error. Like we always know that we have, because the measurement is it's not exactly, and so we always have like a tolerance, like a experimental error.
No, we assume that we model, because we model the error with a Gaussian. We assume that there is a deviation from our deterministic model prediction. Yeah.
Yeah, but I mean, we also have the error where we know, okay, it's only, I mean, the signal is not, I mean, it's not super exact, and we already know what the last point is, or I don't know how to explain. There was also a word because we know. I mean, when I measure with the length or something, I know, okay, my thing is only, I can only measure centimeters or millimeters or something like that. And we also notice for the MR signal, don't we? That we have like a special resolution, and we are not.
Yeah, but we're talking not about space here at all right now, right? So spatial resolution is not here at all, because we're just talking about estimating the contributions of the experimental conditions to the time series of a single voxel, so at a single location. And so talking about spatial stuff will come in when we talk about random field and the distribution of signal over space. So here there's nothing spatial so far.
Okay.
Yeah. Good, then let's stop here.